Hello, science lads. Sorry, I'm always late on because I always leave like brushing my hair and putting makeup on until the last minute because it's really boring. This is the only morning where I've done something even more boring than that, which is why I'm late. I was clipping my privet hedge because I'm 1,000 years old. Anyway, hello, welcome. It's the last waves lesson, the last IGCSE waves lesson ever. Now, we need to do a little bit of something that I haven't taught you, the Doppler effect. And then we're going to do, like, play some games, do a bit of recapping. So I said last week that you only need to know this if you're doing the Cambridge IGCSE. So there's Cambridge or there's like Edexcel Pearson who could write your IGCSE paper. Last week we did signals and you only needed to know any of that really if you were doing Cambridge's paper. But actually I did find a bit about the Doppler effect on the Edexcel one, but it's not in the waves module, it's in the cosmology module for reasons which we will discuss in a second. So I'm glad you all need to know this, whatever IGCSE you're doing. And it's probably one of my favourite physics topics actually. The Doppler effect, right. Imagine that the car alarm of this car is going off, okay? It's just, you know what that means, but I still feel like I need to go beep, 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 beep. So this is obviously what causes the sound. It's vibrations, isn't it? So the car is somehow vibrating the air, kind of pushing and pulling the air, if you like, sending off these kind of pulses, these wave fronts, these like areas of high pressure and low pressure, right? That's what a sound wave is. So it's a little bit like ripples in a pond. Obviously, they're different kinds of waves. But if we say that like this distance here is the wavelength, are you okay with that? The sound wave would just go out into the atmosphere, and if you were floating above the car or if you were in front of the car, behind the car, you'd all hear the sound arrive at the same time and you'd hear the same note everywhere. So the Doppler effect is what happens if something is making a sound and it's moving, right? So if this car was moving this way, then as it's giving off a sound, it's giving off this wavefront, but it's travelled a little bit closer to the wavefront, and then it gives off the wavefront again. It's a little bit closer, but on this side, the waves end up sort of seeming like they get further apart. So you get something like that happening on that side, and that happening on that side. I think it's easy to picture if you think of the car coming towards you. Because quite often when you talk about the Doppler effect, you talk about like ambulances. So if you imagine this car alarm's going off, it's coming towards you. So you hear a sound, but then the next sound you hear the sound waves had less distance to travel. So because it's had less distance to travel, you hear the sound waves they kind of get bunched up basically. So what you hear, if you think of that's the actual sound wave being given off, they come to you faster than they should, if you like, because it's moving towards your ear. So you end up getting something like this. You get a higher frequency. Is that all right? Because the waves get bunched up. If it's a higher frequency, what do you hear? How does this sound wave sound different to this sound wave? I should have done areas of rarefaction, shouldn't I? And areas of compression, but you know what I mean. Yeah, it hasn't really, yeah. How is the frequency different? If it's a higher frequency, then it's a higher note. It's probably easier to draw it as a transverse wave. So that would be like the note as it's coming towards you. And then as it goes away from you, the opposite happens. So it gives off a sound, and then it gives off another sound, but it's a bit farther away. So that sound's got further to travel. So because it's got further to travel, the wavefronts end up getting kind of stretched out like that. And if you remember about pitch, we were looking at pitch. What makes a high note? What makes a low note? A high frequency is a higher note, which is why notice next time like a fire engine or an ambulance comes towards you if you're standing on the pavement, you will hear nino, 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 because the waves are getting bunched up, so it's a high pitch, and then they're getting stretched, it's a lower pitch. Actually no, I'll give you my question. I've got a really evil question for you. I'm so pleased with it. I'm real teacher proud. Everyone on Facebook got this wrong. I think one person out of 2 Facebook lessons got the answer to this. A fire engine emits a sound wave. What about the sound wave changes when the fire engine starts to move? Is it frequency? I've just put some suggestions on the board. Frequency, wavelength, speed. A fire engine emits a sound wave. What about the sound wave changes when the fire engine starts to move? So over on Facebook, nobody was saying speed, and this pleased me greatly because the answer is not speed. I'll show you. I did put it on the screen. It's not any of these things. Did you get that? Not any of them, because obviously, like if this car alarm is going off at a certain note, when the car moves, the note doesn't actually change, does it? Like the frequency of the car the frequency of the car alarm doesn't actually change. So it's not frequency or it's definitely not speed, is it? Because it's traveling through the air. So unless you heat air up or whatever, the speed of sound in air is always going to be the same. None of them. So the next question, so mean. I hope you remember that. What seems to change in that situation? What seems to change? So I was just stealing my husband's mobile phone torch so I could make a rainbow. It's frequency and wavelength as well. If you said frequency, then well done. Obviously, it's the frequency, it's how much something is vibrating that does decide it's how much something is vibrating that decides the frequency. But when you change frequency, if you don't change speed, then you also change the wavelength, right? If the waves get bunched up at a high frequency, then they also have a shorter wavelength. Splendid. So why have EdXL put this in the cosmology section? Well, I don't think we've ever actually made a rainbow doing these GCSE lessons, but a lot of you are coming to my all ages lessons as well, so you've probably seen this before. I've just made it again because I just love it. Wine glass full of water, white piece of paper, mobile phone torch, and you just push the mobile phone torch towards the wine glass. You've all seen me do this before, and you get this gorgeous rainbow. Look at that. So you need to know the colours of the rainbow for your IGCSE physics. Hopefully you all know the colours of the rainbow. Can you remember which one's got the lowest frequency and which one's got the highest frequency? Oh, just stunning. Ah, oh, nature, you beautiful thing. Which one's got the highest frequency? Which carries the most energy? Is it violet light or red light? I'll give you a clue. Red light has got the longest wavelength, right? And violet light has got the shortest wavelength, the highest frequency. So everything, we'll do this in cosmology. I don't want to do too many spoilers, but everything in the universe is moving away from each other, okay? The universe is expanding. You can imagine that all the stars are like dots on a balloon, all the galaxies are dots on a balloon, and the balloon is being blown up, so everything's expanding. So scientists were amazed when they looked into the sky and they noticed that all the stars were moving away. And it's what you call redshift, because if you think of the light that a star is giving off, if that star is travelling away from you, then kind of the same thing as with the sound. The light is stretching. Yeah, and this is called redshift, which you do need to know about for your EdXL. We'll do cosmology right at the end, but it kind of fits in with the Doppler effect. They're sort of the same thing, but redshift is light and the Doppler effect is sound. Well, Doppler effect could be light as well. Can you think of a situation, like really the only situation where you get something called blue shift? So everything in the universe is moving away. So everything you look at from Earth, it seems like things are moving away from you. So everything is red shifted. It doesn't mean that things are red, but like if a star was giving off blue light, say, then it might look a little bit more greeny because that blue wave of light had been sort of stretched a bit. Can you think of anything where it's the opposite, where something might be moving towards Earth? So the wavelength that it was giving off would be sort of slightly squished and it would seem a bit bluer. There's no reason why you would, because this isn't cosmology. We haven't done cosmology yet. But I'll draw my stars like this. Actually, it's really common for stars to be two stars orbiting each other, like a binary star. So stars that are orbiting each other, there is a point where, if you imagine that you're on Earth, which is the camera, there's a point where one star will be orbiting the other and coming towards Earth. So some stars can be slightly blue shifted because they're doing that, but otherwise everything's red shifted. But anyway, that's the Doppler effect. let's move on to our recap. Should we play some bingo? If you've got the sheet, if you've downloaded the PDF from my Facebook group, you've got no problems, you can just do this. If you haven't got the sheet and you want to play bingo, all you have to do now, please, is can you draw 3 lines down and 4 lines across, like that? Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, you need a grid of 16. Yeah, that's fine, isn't it? I guess you could do. Just draw 16 squares, please. Just draw a quick grid. You don't need to write all the words inside, but I'm going to read out some questions. And when you see the answer, I want you to cross it off your grid. If you haven't got the sheet, just put it in the right box. So if you think the answer is, well, I'll show you. Like, if you think the answer's radio, just put a cross in your top left box, right? Don't bother to write out all the words. Up and down counts, across counts, diagonal counts. So I'll read out a word, cross off the right answer, and then when you get 4 in a row, I don't know, shout bingo in your head. Let's see how we get on. You ready? So, number 1, what do waves transfer from one place to another? What do waves transfer from one place to another? Is it from top to bottom, left to right? Radio speed transfers wood, amplitude, longitude, wavelength. 1, sound, vacuum, energy. 2, matter, glass. 4, light. What do waves transfer from one place to the other? Right, moving on. What kind of wave is this? Not give me an example of that kind of wave, just what is that kind of wave? What do you call that kind of wave? Radio speed transfers wood, amplitude, longitudinal. Microwave. 1, sound, vacuum, energy. 2, matter, glass. 4, light. Moving on. And how many wavelengths are shown here? I think this is quite hard. You've got a wave that starts at the very top, goes all the way down, all the way up again, all the way down, all the way up again, and then that's it. So it starts at the top, goes right down, right up, right down, right up. How many wavelengths is that? Is it 1, 2, or 4? Moving on. Which one of these is an example of a longitudinal wave? There's only one longitudinal wave on this grid. Which one is it? Is it radio speed transfers wood, amplitude, longitudinal, microwave? 1, sound, vacuum, energy. 2, matter, glass. 4, or light. Which one of those is a longitudinal wave? I'm sorry about my dripping tap. It sounds like I'm teaching from a cave. We have got a plumber coming on Friday. Next question. Which one of these is the wave used by mobile phone signals? Which wave gets used by mobile phone signals? Is it radio speed transfer? Come on. Which one gets used by mobile phones? This was perplexing a few people on Facebook. Okay, moving on. I don't know if anyone's got a bingo yet because there's no comments on YouTube. Sound cannot travel through this. Sound cannot travel through this. What cannot sound travel through? Radio speed transfers with amplitude, longitudinal, microwave. 1, sound, vacuum, energy. 2, matter, glass. 4, light. Okay, you should be shouting bingo. Let's go through it. What do waves transfer from one place to another? It is energy. On the Cambridge spec, they say information as well. Waves carry information, or they can do, but on the EdXL spec, they just stick with just energy. It's not matter, is the important thing. What kind of wave is this? That is a transverse wave, the wiggly, wormy one. How many wavelengths are shown here? It's 2 wavelengths, right? Because you count until... one wavelength is you go until you're repeating yourself. So all the way up, all the way down, all the way up again, that's 1. And then you've started to repeat all the way down, all the way up again, and that is 2. An example of a longitudinal wave is sound. That's the only one that is longitudinal. The wave used by mobile phone signals, that is microwaves. And sound can't travel through a vacuum because it needs particles to travel, and a vacuum is a place where there are no particles. Well done if you got that. Right, should we play let's play a quick game of what's the word? So I've got the electromagnetic spectrum, you know, the waves that travel through space at the speed of light. I've put a letter next to each of them, and I've given you some clues, and you need to choose the letter that matches the answer, and then tell me what word you've got, all right? So if the answer's radio, write an R. If it's microwave, write an H. If it's infrared, write a T. If it's light, write an I. If it's ultraviolet, write an E. If it's X-ray, write a D. And if it's gamma, write an S. So which one of those waves carries the most energy? That's your first letter. Which one carries mobile phone signals? I literally told you like 8 seconds ago, so hopefully you get that one. Which one is not X-ray and it's not gamma, but it is ionizing? Which one of those has got a slightly higher frequency than light you can see? And you mainly give off these waves. Which one's that? You mainly give off these waves. Five seconds. Okay, which one carries the most energy? It is gamma radiation. It's the most dangerous. It's the one with the highest frequency. It's microwaves that carry mobile phone signals. Hopefully you remember that now. You remember because we've talked about how microwaves carry mobile phone signals because they're good at travelling through walls. They're pretty good at getting through stuff. But radio waves can do that too, but radio waves would need a massive antennae to emit and detect waves. So it's if you use a microwave, you can have a smaller aerial, which is good for mobile phones. Not X-ray and not gamma, but it is ionizing. That was ultraviolet. That's the only one with enough energy to really damage your cells. Slightly higher frequency than light you can see is also ultraviolet, right? So this is light, and it's got a slightly higher frequency. And you mainly give off this waves. It is infrared. So the word was sheet. Although I didn't know until I started teaching this lesson that we also give off microwaves, but we give off kind of quite long wavelength infrared light, and it does bleed into microwaves as well. Awesome. Right, one more, guess the word. Here's your clues this time. Which wave is used for detecting and treating cancer? Which one's got a slightly longer wavelength than infrared? Which one's used in photography? Which one carries the least energy? And which one's used for TV remote controls? 6 seconds. Right, which one's used for detecting and treating cancer? That is gamma radiation. It is a slightly weird one, that, isn't it? It's like, why? How can it do both? Basically, gamma radiation just carries an awful lot of energy and damages cells. So if it can damage healthy cells, but also if the cells are cancerous, it can be used to damage the cancerous cells on purpose. So yeah, it treats and it detects cancer, which does seem slightly odd. Slightly longer wavelength than infrared. Infrared's there, so the slightly longer wavelength is a microwave. So we've got SH. Used in photography, that's light. Sort of seems obvious, but you do need to know that. Which one carries the least energy? Radio waves, travelling right through you now. Can't even feel them. And which one's used for TV remote controls? That is infrared. So the word was shirt. Well done if you got that. Okay, get a pen and paper, please. Pen and paper, you got a pen and paper? Oh, wait. No, you don't need pen and paper yet. We'll do this first. Here we go. I have drawn a terrible diagram of someone seeing a duck on a high shelf above them in a mirror. Can you pick out, either with a pen or if you're just looking at the screen, with your eyes, all the mistakes that I've made in this diagram? So this is how a person sees a duck, which is like on a shelf above them. But what have I done wrong? And can you draw or imagine the image in the right place? So where is this is the actual real duck, and that's the mirror. Where is the image of the duck? I'm going to count 20 seconds in my head. So where's the image and how big is the image going to be? You ready? There it is. So it's the same size, right? This isn't lenses, so it's going to be the same size as the actual object. And it's the same distance away from the mirror as the actual object is from the mirror, okay? Hopefully you remembered that, and it's flipped, obviously, it's a mirror. Did you all get the Superman eyes? This is not how seeing things works. Light does not come out of your eyes and hit the thing that you are seeing. Light has to bounce off the duck and into this person's eyes. Well done if you got that these angles are in the wrong place as well. And just be very fussy, those normals are wrong as well. Let's draw what it should look like. So light should be bouncing from the duck off the mirror and into the eye. That is better. The normals should really be dotted, technically. And the angles are between the rays and the normal. Otherwise, what are you bothering to draw the normal for? So that's the angle of incidence, because this is the incident ray, the one bouncing on. And this is the angle of reflection, because it's being reflected, right? It's a reflected ray. Yes, right. Now you need pen and paper. You need pen and paper. I've got some 15-second challenges for you. I think I've got 4 of them. Quick, pen and paper. Get it? You need to practice fast writing anyway for the exam. I'm going to give you 15 seconds to... Got pen and paper? Okay, let's go. Name these pieces of equipment. I have to say this was very poorly done on Facebook yesterday. See if you can do better. 15, 14, 13, 3, 2, you got them all? 1. If you haven't got them all, then yeah, you are not alone. So this was a ripple tank. Most people on Facebook got that. Quite a lot of people calling this a ray box. I've put light box for the middle one. And this last one, I was getting some really fascinating answers. Oscilloscope. So a lot of people were saying oscillator. An oscilloscope measures things that oscillate, just like a microscope measures things that are micro. Yeah, that is an oscilloscope. Right, 15 seconds. Can you write down as many transverse waves as you can? I definitely don't think you're going to get one of them. How many transverse waves can you think of in 15 seconds? You got 10 seconds now. Three, 2, 1. All right, so you could have had any of the electromagnetic spectrum. Well done if you got all those, because they're all the same, right? They all travel at the same speed, the speed of light through a vacuum. It's just a frequency really that's different. You could have had S waves that travel through the earth during earthquakes. You do need to know that, actually. Yeah, we talked about it in the earthquakes lesson that I did for all ages, but we haven't really mentioned it yet, but they are transverse waves. Ocean waves would be a good one. Or you could have had slinky, as long as you explained why. Like if you said a slinky where the vibrations are at right angles to the direction that the energy is travelling in, then that would have been fine. Okay, 15 seconds to write the waves of the electromagnetic spectrum in order. You might have just done this. Write the waves of the electromagnetic spectrum in order, please. In order of frequency or wavelength. 15, 14, 13, 12. Three, 2, 1. Did you manage it? Radio, microwave, infrared light, ultraviolet, X-ray, and gamma. That would be such a nice question if they just give you that and there's 2 missing and you have to fill in the gaps. It sometimes happens. Okay, and the last one, you've got 15 seconds, please, to write down as many words as you can that relate to what you see here. I'm laughing because, again, on Facebook, really, very dreadfully done. So you've got, what is this? It's like a small tube, which is kind of glowing red, and you've got what looks like a laser bouncing around inside the tube, bouncing along the tube. Yeah, what words can you, what is that? What is it used for? What phenomenon is happening inside? Physics words, please. I don't just want red, tube. What is that? What's happening? What is it used for? 15, 14, 13, 12. I'll give you a clue. A lot of people on Facebook were saying reflection. And I was saying, yes, not enough. What kind of reflection? 7, 6, 5. You might have put different things. I put fibre optics because that's what that is. It's a fibre optic cable or whatever, just a very thin tube made of glass, or usually now plastic that behaves the same way of glass. It's total internal reflection that's happening in there. I wrote signal because it carries, usually digital signals. It could carry analog signals as well. And it's used for TV and internet to carry the signal from one to the other. Right, should we do an activity? Because I did say to bring a balloon and a 50p or 20p. You might well not have had those things. I'm not sure that either of these are household objects anymore, to be honest with you. But what you have to do, first of all, I'm going to do... Yeah, actually, no, I'll do it with the 20p first. So what you have to do, if you have found a coin and a balloon, is put the coin inside the balloon. It's really easier said than done. Put the coin inside the balloon. There we go. And then blow the balloon up. And then I'll show you what we do next. Oh, God, I hate blowing up balloons. Whoa. Okay. I can do this, just one more. Whoa. Whoa. Right. The hardest bit actually is you want to be able to reuse the balloon. So you've got to somehow be able to hold the balloon at the top so that you can spin it around. So if you sort of wrap it around your finger so that you can hold it like that. And then here's what happens. If you haven't, you can just watch me obviously if you're not doing this. So 50p, no, I've got 20p, you could put either in. 20p inside this balloon, blow it up, gonna give it a spin. And then let go. Isn't it? I'm going to do it one more time. So why does that happen? This is my question to you, IGCSE physicists. You should have quite a lot to say about this by the end of our waves module. Why does that happen? What is happening for a start? What do you observe? Well, you're hearing a sound, right? And the sound is getting lower. So why are you hearing a sound? And why is the sound getting lower? Why are you hearing a sound? Why is the sound getting lower? Incredibly irritating that there's no comments on this video, so you can't actually tell me. But have a think, and then I'll tell you what they said on Facebook. Saying it out loud, it might help to say it out loud. So, some people on Facebook, so I was pleased about, it's awful when people get the right answer. I'm like, why are you here? I'm not teaching you anything. Some people saying friction. So friction, like the coin rubbing against the balloon, is what is making the sound. And I said, oh, what a brilliant idea. I'll tell you what, I'll get a 2p and I'll put that in the balloon because there will be friction between the 2p and the balloon as well, right? So we'll see if it's friction making the noise. Right, so I'll do the same thing with a 2p. Did you see that? It was going round. It's not that it's not working. Barely a sound. So it's not friction, is it? It can't be friction. Why? Why does a 50p make a sound? Did I just write that backwards? Hopefully not. I'm awful at writing backwards because I teach more on Facebook than I do on YouTube. Why does a 50p make a sound? And a 2p doesn't? And why does the sound get lower? While you're thinking it through, I'm going to try it. Oh, no, wait. We used the 20p, didn't we? Because I wanted to save the 50p till last. So now I'll do it with the 50p, and we'll see if there's a difference. And what difference are you expecting to hear? If you are expecting to hear a difference, will there be a difference when it's a 50p and not a 20p? And if so, what difference are you expecting to hear? Ugh. Right. Let's have a go. So 50p now. So good. What's the difference? I think it's slightly louder. So the answer that I've got is, well, why does anything make a sound? It's got to be vibrations, hasn't it? So it must be that a 20p is making the balloon vibrate in a way that the 2p isn't. So it's because it's got corners, basically, as it's the corners knocking against the balloon are what's making the balloon vibrate the air, which is what's creating the sound wave. So if you've put anything to do with vibrations, well done, I would totally agree with you. Yeah, so that's why the 2p isn't making the balloon vibrate in the same way. It's just sort of in constant contact with the balloon. And the reason that it's getting lower is because it's slowing down, right? So the pitch of the note getting lower means that the frequency of the vibrations is getting lower. It's vibrating fewer times per second. So as the coin sort of loses energy and slows down, it's hitting the balloon more slowly, right? So the balloon's vibrating more slowly, And fewer vibrations per second means a lower pitch. Is that okay? Someone on Facebook did an absolutely brilliant answer that would have got 0 marks at GCSE because it was like, oh, the balloon changes speed and therefore the frequency changes. And it's like, you know exactly what you mean, but actually you haven't said how it changes. You've just said that it changes. Okay, right, last question. Yeah, last question, here we go. I'm very pleased with this question. It's like a 4-part question and then we'll finish. You shouldn't need a calculator for this one, really. A teacher writes this question for her class. A ship is measuring the depth of the ocean floor. It emits a sound wave which returns in 4 seconds. The speed of sound is 340 metres per second. How deep is the ocean below the ship? So that's worth 3 marks. So what I'd like you to do, please, is answer the question and then say, why is the answer incorrect? What mistake has the teacher made? And then say, would the correct answer be higher or lower? And then suggest a suitable frequency for the sound wave the ship used. I've really got my smug teacher face on. I'm very pleased with this question. Ship is measuring the depth of the ocean floor. It emits a sound wave which returns in 4 seconds. The speed of sound is 340 metres per second. How deep is the ocean below the ship? So answer that question. Tell me why that answer is wrong and what mistake the teacher's made. And would the correct answer, would you expect it to be higher or lower than your answer? And give me a frequency that the ship might have used for that sound wave. I'll do it with you on the board so that I can pace your thinking time correctly. I am collecting this water, by the way, if it's really annoying you, that the sound of the drip and the idea of water being wasted. In September, it'll all be sorted. How you getting on? I'll try and do something about this tap, just the noise. So I'll give you about 15 seconds and then we'll go through it. All right, let's have a look then. So, did you remember that if a sound wave takes 4 seconds to to go down to the bottom of the ocean and then bounce back and come back to the ship again, you got to halve the amount of time to find out how deep the ocean is. So it takes 4 seconds to go and then all the way back again. But you only want to measure this distance from here to here. So if you're going to use the equation speed equals distance divided by time, then you want to find this distance. So the time it's taken the sound to travel that distance is only 2 seconds. So I've written speed equals distance divided by time. We're looking for the distance. We want to know how deep the ocean is at this point. So I've rearranged it to distance equals speed times time. And then we've got the time. We've got 2 seconds. The teacher's given us the speed, 340 metres per second. So you just put those in and you get the answer, 680 metres. Except that is not correct. I hope you are screaming at the screen. They've given us the sound of the speed of sound in air, but this is water. So air particles, a lot of energy, far apart, quite an inefficient way for sound to travel. The sound particles have kind of got to move quite a long way to get to each other, to bump into each other, to carry the sound. Water particles are touching each other, so they carry sound much more quickly. Sound travels faster in water. So if it's taken 2 seconds for the sound wave to get to the floor, but it was actually travelling a lot faster than the ship thinks, or than the teacher thought. If it's travelling faster, but it takes 2 seconds, is the ocean floor going to be deeper or shallower? Well, it's gone faster, so it's travelled more distance in that time. So this answer is going to be actually higher. And oh yeah, so the incorrect answer was because of this. It was the speed of sound in air and not water. The answer would be higher. And for the frequency of sound that the ship might be using, if you've put anything above, what am I going to say? What did it need to be over? So the ship is using ultrasound, right? And ultrasound is sound that humans can't hear. And humans can't hear sounds above 20,000 for 1 mark, hertz for your second mark. 20,000 vibrations per second is the absolute max that the finest human ears can hear. Oh, well done if you got all that. Right, that is the end of our IGCSE lessons on waves. So we're doing well, aren't we? We've done forces and motion, we've done electricity, we've finished waves. I'm working to the order of the EdXL spec. So next term, I'm going to start on energy, solar panels, like different kind of forms of energy and energy transfers. Yeah, it's going to be good. I can't believe it. I can't believe we're nearly halfway through. If you want to support me, if you're enjoying these, you totally can. I very much appreciate people paying my wages, or I could not do this job. So you can go to my coffee page, which is, actually I think it's in the comments. I've started putting it in the comments to make it a bit easier. So if you go to the comment section, you can click the link there, and it takes you to this website called Coffee, where you can, if you want, send me £5 a month, and I will be desperately grateful, and I will send you nice things to say thank you for paying my wages, because this is the best job ever. Right, I'm just going to go to my Facebook page and see if anyone has said hello to me. And then I better go, because we've only got 10 minutes, and then the All Ages Coral Reefs lesson is starting on Facebook. Oh, brilliant. Look, some comments. This is my holding music while you wait. Oh, Bastian will be watching later. Hello, Bastian. I can't imagine you've got this far, but hello, Bastian. If you watched till the very end, hello. Thanks for watching, dude. The frequency seems to change. Oh, hello, A. Well done. Correct. Yes, excellent. Oh, and Sky and Evie and Honey are here. Hello, happy Science Day. You're not. Oh, that's nice. Splendid. Oh, wait, there's one more. There's one more. Oh, it's Tiger and Birds. Hello, Tiger and Birds. Hello. Right. Oh, thank you so much. It's really nice to know who's watching. I will go and get ready for the last coral reefs lesson. I get to show off my fossils. I really enjoyed this topic. All right. Yeah. See you. So if you come to my Lego Storytime shows, which I think you do, then there's one more tomorrow. And if you don't, then that's it. I've got 6 weeks of summer holiday now to frantically plan and also write my sports magazine. And then they'll start again in September. I think the week of September the 4th is when these lessons start again. So yeah, if I'm not going to see you again, have a wonderful summer. Bye.